This week on FX Guide TV.
We head to New Zealand, where we celebrate the award-winning work of the team at Weta that developed Tissue, a physically based character simulation framework, the winner of the Science and Engineering Award at this year's Sci-Tech Oscars.
This and more coming up next.
Hello, I'm Angie Dale and thank you for joining us. Before we start the show, I just want to thank our Twitter fans. FX Guide TV has grown and grown, but as the show kind of comes out roughly every 2 weeks rather than on an exact day, we have grown to rely on you guys retweeting the show and posting it on Facebook to spread the word. In fact, we've kind of really come to rely on it. So thank you very, very much. All right, now back to the show. We have a very special one for you this week, but I'll let Mike explain.
Well, this year's Sci-Tech Awards, Weta was featured for its work with Tissue, which is an incredibly interesting physics-based simulation creature tool. We sat down with the guys here at Weta in Wellington, New Zealand, to talk about this incredibly interesting and really innovative way of doing character work. So thanks so much for joining us, we really appreciate it. So tell me about Tissue, and when did it first come into your kind of pipeline?
Yeah, it's kind of during Avatar, around 2008. We were sort of requested to develop something a little bit better than the current tool set that was being used on the movie. They weren't, like Joe wasn't particularly happy with the current look of the hero characters. And I had developed sort of a finite-element model system as a toy, just kind of something I was interested in doing. And we kind of took that and then ended up expanding on that to build like effectively a new sort of physically based muscle and skin system. So sort of the early development was sort of 2008, 2009, and then it ended up being used on its first sort of major outage was the primary characters on Avatar, so Jake and Neytiri.
Yeah, because Jake or his avatar is effectively naked or pretty much, so you get a lot of chance to see what's going on. It's not like it's a cloth sim hidden problem. So tell me about the two components of it, because there's really two aspects to it, isn't it? There's this idea of the simulation and getting realism in there, but also the idea of how the animators work with it in terms of it working with this. Let's start with just the physics of how it works.
Yeah.
So what is it trying to do, and how did you do it before you had it?
So the previous approaches, and I think that's approaches sort of adopted by other studios and sort of character rigging in general, is to have an approximation of some kind of underlying anatomical object. So typically like Maya muscle, comet muscle, these things, would be like a tube effectively with some control points on it, and people parent them to joints and then, sort of go to a pose and set the shape of that thing. And Weta had developed something really similar to that way back for the first Rings movies. So they had this Weta muscle primitive, and that's all very well and good, except there's no real physical basis, right? So it doesn't really have kind of it's a geometric model, it's not a physical model, right? So it's not, and what we wanted to move to was a physical basis for all the creatures to gain more realism, and also importantly do things computationally. So just let the computer do the heavy lifting rather than character TDs having to be in there.
Well, let's explain it in terms of, say, a bicep, because that's a pretty easy thing to understand. Okay, so firstly, it isn't volume preserving, because a bicep isn't volume preserving. It actually obviously changes its...
So muscles are volume conserving. In fact, they're almost completely volume conserving. So when a muscle contracts, these little myofibril links, they start to interlock together, and that shortens the muscle. And you get this transverse bulging because effectively right down on the sort of smallest level, these fibers are full of blood. And blood's a liquid and it's highly incompressible. So they're not 100% volume preserving, but we actually got the real numbers because the Poisson ratio in our model, which dictates how volume preserving something is, it's almost completely incompressible. So what we end up with, what we have is we have our bicep shape, and a TD can model that just with polygonal models in Maya, basically just make any shape they like. They then tetrahedralize that model, and then we have tools to basically describe the fiber field within that tetrahedralized volume. And then when you say this muscle is activated, the fibers cause the tetrahedra to contract, and then you get transverse bulging.
Right, but it's sort of, I guess, the inverse of what actually happens. So I would bend the arm, causing the muscle to look like it's...
Yeah, we solve the
opposed-
inverse problem.
Yes.
So we all our input is kinematic animation from the animation department. So they have a low-res puppet. They don't see any of this stuff. They basically just see a almost like a pre-visualization puppet. It's just parented bits of geometry onto a very simple skeleton, and they animate away. That's cached, and that drives like an up-res polygonal representation of the creature's skeleton, and all the muscles are attached to that, and we solve out the inverse. Yeah. So instead of saying the muscle's contracted, which applies a force to the joint and makes the joint bend, we say, well, here's the joint bending moments over time, and we figure out how much force to apply to the muscle to make it contract.
But isn't there also another aspect to it that handles the simulation of what the flesh would effectively do under physics environments?
Yep. So the tool set effectively, the same tools can represent all the different biological tissues. So the tissue can be used to create like skeletal, like muscles, or it can be used to create skin or fat or tendons. And so the one tool set, we describe all the layers with it. So typically a creature has a bunch of these tetrahedralized muscles with fibers in. They also have a fat layer and a skin layer, and they have tendons and other bits and bobs, and a fascia layer. And all that's basically simmed together to produce the final cached polygonal outer model that's sent to the renderer.
So that outer model is taking account of those things that would have what I'm going to call a lateral movement in a way that a muscle wouldn't. Like, a bicep doesn't wobble and it's contracted in the way that fat does, for example, right?
Yeah.
But skin also travels over, and that skin travelling over was always the thing that defeated us in the early days of animation. And it just never felt like there was anything under the skin.
Yeah, and typically, we've spent years now sort of doing. We've partnered with biomechanics researchers and veterinary colleges, and we've done a whole bunch of work on a lot of these anatomical effects. And the misconception with skin sliding is that A, there's anything sliding, and B, it's the skin. So typically it's not. So there are two major feature things happening for skin sliding. One is basically your skin is attached to effectively like this sort of, I think, subdermal layer, which is basically we represent as the fat, and that's stuck to this fascia layer, and the muscles free slide under the fascia, right? So they're the big form changes that you see. Like if you look at someone's back, the scapular blade and all this stuff is moving under this like elastic sheet. We basically definitely approximate this because it's a lot more complicated, but in the approximations, that's kind of what's happening. And then your skin's really tough compared to this subdermal layer. So when you effectively stretch your skin, the subdermal layer can shear, and that gives you this fine feature motion. So your skin's not sliding, it's effectively the fat compressing in this shearing motion that gives you these travels of features. So these two main things, and we did the same before as well. People kind of bundle that up and call it skin sliding, and the normal approach is to take your approximate muscle thing and effectively project it to the surface and have your surface slide over it. But because we went and sort of modeled all these anatomical layers, we kind of went back to the textbooks and realized, actually we can represent the real way the skin actually behaves.
So when we get to the face in particular, are all these same things applying? Because you said that, I'd said that muscle was not volume preserving, you corrected me, but I would have thought at the face level, you get a rush of blood to the face, which causes a lot of things. Is that so subtle that we're reading it for colour but not reading it for actual volume, or are there actually sort of veins popping? Is that literally happening?
So yeah, the face. Again, we've looked into. Well, we've spent years now doing facial development work. It's a lot more complicated than the body, because the muscles, like typically you can sort of simplify the body down to, we've got skeletal muscular structures, like the main ones you can see, and then we've got this sort of fascia layer, and then we've got these layers of skin. But in the face, the muscles actually travel through all these different layers. So you've got these muscles that are basically like threads in some places, and in other places they're kind of represented like how you see them in the anatomy book, like the orbital and the zygomatic are all kind of like these sheet muscles. The use for tissue in the facial stuff, its use for is not to, currently we're not solving the facial animation. That's being done as like a blend shape network, like the traditional way. But what we do is layer on effects on top of that. So for apes, Caesar has, all the chimpanzees have these really wrinkly muzzles. Well, that's all sim. So we effectively wrote a constraint in tissue that could track the input animation. And then we built these really high resolution, multi-layer tetrahedralization models that solved all the skin wrinkling. Because it's like this sort of combinational problem. Like you don't want to model like thousands of blend shapes for every potential combination of that rubbery muzzle to give you the wrinkles. So we just sim them all. So we were using it on the faces, but not for the primary performance.
Right. And what about hands? So there's another big thing that's obviously very important to a lot of action. Now I'm not a medical student, but I understand I don't actually have muscles in my fingers, right? So this idea of, we're talking about muscles, but obviously it extends beyond that, as you've indicated, because otherwise I couldn't do this.
Yeah, so we have another model. We have basically a tendon model, which we had a student come in to implement, biomechanics guy. So we've got this strand model where you can represent, basically you can do force transfer down very thin objects. So we did build the hands with tissue. I mean, James can talk more about this. One big part of tissue is that we're using it to train pose-weighted deformers so that we can encapsulate like big ranges of motion that are simulated and then replay them, basically reuse them without having to resim, and that's how the hands were done. They're basically sort of part tissue and then part sort of deformers and then cached. But we could we're representing. They're basically built the same. Pretty much everything is built the same with these same components.
So I come to you with a new film, and it's got a bunch of CG characters in it, so we're not talking about people. It's probably likely that the character designer had a body of sort of backstory of whether it's a carnivore or a herbivore, and that's influenced how they've designed the character, but they're almost probably designed that character from the outside. Yeah. Does a team then have to work out what the relevant biomechanics must possibly be? Yeah. So typically, like most of the invent the anatomy.
Yeah. So most of the creature design, I mean, that we've come across has groundings in something. So it either looks like a bit of a horse mixed with a crocodile, or if you look at sort of generally a fantastical creature, you can derive like, the hip of that looks a bit like the hip of a horse, and
right. And if it's a predator, it's going to be able to have more sort of eyes closer together. A herbivore's going to have them. And so basically,
I mean, it's cool with made-up animals because then no one's there to tell you if it looks wrong, right? So there's part of it's like we tend to end up with fitters. We start with a skeleton and we fit a skeleton. So there's the rib cage and the pelvis, and this is where the shoulders are going to be, and we try and basically fit an animal skeleton, whether it's like we start with a quadruped or a biped skeleton, to the fantastical creature, and then we basically sort of take known muscle groups and then fit them, and then just figure it out from there. But yeah, we just tend to kind of do a best fit, really, kind of what looks cool.
What looks cool, but also there are considerations of like weight, because obviously depending on a creature's weight and its mass distribution is going to heavily affect the amount of muscle it needs. And you must, I mean, obviously you get to a point where somebody just thinks it looks really cool to have a really huge character with tiny legs, and you can fake it, of course, because it's filmmaking. But there must be kind of quite a lot of, I guess, anatomical backstory into sort of how you put it together.
Yeah, I mean, the advantage, there's anatomical correctness in the system, which is cool. The other advantage is that even if you do something kind of like when we worked on Prometheus and we made the big crazy face hugger tentacle beast thing that has no real basis on anything, we can still use tissue because there's other advantages too, like it handles the collision detection, the volume preservation. So even making like a big crazy tentacle beast monster, it may be anatomically not viable, but you're still getting the advantages of sim because you're not having to do, you get a lot of stuff out for free effectively, which normally you'd have had to handle with like a straight deformer based setup.
And I'm guessing I'm also getting just simple stuff, like if some character has a big jowl, I'm getting a lot of that secondary motion with a lot more realism. But presumably you need to then also build in a lot of controls because again, it might be anatomically and mathematically correct to flap around, but that may be distracting.
So one of the things that was developed really early on during Avatar is sort of the realization that we could have these great anatomical systems and the physics are great, and then we get a piece of animation where a character's doing like 3,000 kilometers a second, right, through the frame. So and that's what the director wants. So tissue works on the premise that it has basically custom spaces you solve everything in. So if you've got a character and he's whizzing through the frame at 1,000,000 miles an hour, you can actually tell the solver that isn't how fast he's moving through the frame.
So you're changing the environment that the physics is happening in rather than tweaking the physics of the response to the environment.
Yeah, so we're basically saying, so a good example of that is, say.
Or someone's pulling out a big G of a flying on
Yeah,
a
well,
flying creature.
like there's a shot in Avatar where Jake just jumps off a cliff, or he goes down the side of the cliff on the Banshee, right? So to the solver, he was not moving at all. He's only moving locally within his own local frame. So his arms are moving, and his legs are moving, and his head's moving, but he's actually not moving through space. And then what we can do is we compute the velocities off the animation, and we can dial bits back in. So there's a shot in Apes where Rocket is going crazy on the cage. He's like jumped up on the side of the cage, and we can effectively just inherit some of that motion, or as much as we want.
Because that's the second stage I wanted to talk about, that idea of the animator using it, because the animator can to a certain extent ignore it, but as you're saying here, they can also, and I mean by that, ignore it in the good way, in that it does what it's meant to do, but then it can also be overwritten, and that's how they're doing it, right? They're just overriding the environment in which this character or part of a character is existing. I mean, could I override it on, say, the face doesn't get deformed, but the body does?
Yeah, it's like we call them frames, and you can basically apply frames to parts of the character, the whole character, or individual vertices of the skin. Or, interestingly though, a lot of the ape shots, because everything is simulated, right? So again, and James is a good person to talk about this, because we only ever build one creature. In fact, we only ever build half of one creature, and then everything is geometrically warped to create the other half, and then that archetype is geometrically warped to create all the other types. So every chimp in Apes was derived from one build. And there's shots of dozens and dozens of apes running down the road and stuff like that. They're all simulated, and actually they didn't have frames at all. That's all inheriting world motion and stuff. So Richard Dorling, who's also one of the collaborators on the framework, he made it hugely more robust after Avatar, and so it could cope with a lot more.
So James, thanks for joining us. Talk to me about the simulation side of what's happening with tissue. Like, how far does that simulation go, and is it just based on mass? What's the in terms of gravity and?
Yeah, well, it takes into account all sort of typical physical parameters that you'd be interested in. So like there's the density of the object that we're dealing with, which is how it reacts to inertia and how it's moving through space and stuff like that, and the stiffness of the object. So how easy it is to stretch it and for it to go have elastic deformation. And then there's the volume conserving aspect of it. So how volume conserving it is. So if its Poisson ratio is quite high, it's not going to, when you squeeze it, you'll get a transverse bulge. And then it will react to gravity. And pretty much, I guess that's the basic stuff. But then we also have a variety of constraints that we've written that you can apply to it as well, like to make it behave in novel ways. So typically when you're building an anatomical model, you'll use a variety of constraints like rigid pins to attach muscles to parts, or we have rotators, so ones that will, sort of constraints that are, a Lagrangian type pin, so it can rotate, but it will maintain an offset from the point where it's attached to. We have implicit springs and sliding constraints and sliding springs, and and then there's also a sort of a plug-in framework where TDs can write their own fields or anything like that they want to interact with the simulation.
So let me ask you about hands, because I don't actually have muscles in my fingers, so I tend to colloquially think that I have muscles in my fingers because they contract like a muscle would. But what's going on there, and how are you dealing with it?
So earlier in the year, we had a grad student here, and he'd implemented a one-dimensional element into our system matrix. So most of the things that we're solving are three-dimensional elements. So our muscles and skin and fat are all typically tetrahedra. And we have two-dimensional elements which we're solving, in the case of the fascia, and then the one-dimensional ones, in the case of the tendon, like what you're saying with the finger, it allows us to transmit force from one point just to another. So in the case when you'll bend your finger, it'll be able to transmit force just along that to the muscle that it's actually attached to. And you're saying transmit
the force because it's the reverse, right? Because you bend the finger, we want to see what caused it, not what causing
exactly.
it.
Exactly, but interestingly, you can actually run the system the right way around too, but it's just our input to the departments typically, it's always like Sun was saying, a kinematic motion is input, but you could actually run it the other way and articulate a hand by firing the muscles as well, which is kind of neat.
But much harder to animate with.
Much harder to animate with,
So tell me about the computational cost of doing this, because if I'm an artist and somebody comes up with a great system, that's all well and good, but can I use it in an environment where I can see what the results are, or is this simulation going to take a lot of time and I've got to come back later?
Yeah, well, I guess typically, what the stuff we're building that's using this, it's the way the sort of the animation pipeline works here. Like as Simon explained earlier, we have the animators have a low-res sort of approximation of what the character looks like, so they're able to pose him interactively. So I guess like there's each department has its own requirements. So animators need things to be really fast and interactive in order to most easily get a performance across, and we need things to be more accurate in order to look correct, and how fast it is less important for us. So typically when we're running a simulation, that's hours to run a simulation on a character. But we have ways to make it run quicker, of course. Like we can use a simulation as a training basis in order to build like a post-space deformation from like a large simulation. And then that's much more interactive if someone could actually pose that at near interactive rates.
So they're going to do a pose, and there'll be some form of deformation to give me some idea what's going on with the muscle, but we don't really care if it's that accurate right now, just that there's something to give back to the animator.
Yeah, I mean, typically with muscle bulging and stuff that's not performance related, we're not too concerned about representing that in the puppet, or we haven't been. But things that are performance moments, like when they're flexing a muscle in order to indicate a performance beat, then we have controls in the puppet that they can dial in, and they'll see a blend shape that is usually built directly off of the resulting shape of the simulation, so they can see what it will look like, at least at that moment, and then set some keyframes, and then those keyframes get passed into the solver that then get solved out, so you get the proper sort of motion between those sort of poses.
So I can imagine this being terrific if I'm doing just straight character work, but I can also imagine this really coming to its own if I'm trying to do digital doubles, because at some point I'm trying to blend from maybe an actor to this model, and carrying that forward is going to help a lot with the realism, I imagine. Yeah,
it's been really helpful actually. Like, although say in the case of Tintin, it wasn't the characters weren't realistic looking, but I mean, if their clothing was quite realistic, and the way it draped on them was quite realistic, and all those characters benefited from the fact that their underlying sort of body shape was much deformed, much more like what a real body would. And in the case of, all our digidoubles also benefit from the same thing. Like we have very complicated costuming on The Hobbit, and it all benefits from having something underneath that just is a better approximation for a real body than what has been done in the past.
Right, so in an avatar situation, I'm really concerned with that look, because I'm going to see the character. But you're reading it strongly under their clothes in terms of how their clothes are draping on them.
For sure. The way your jacket sits on you is directly affected by the shape of the skin underneath. So.
And how far away from just a quadruped or a biped have you got? I mean, can you apply this sort of further afield?
It lends a lot of physicality to any sort of creation that you have, because it's with the volume conserving nature of it, and just the fact that it's a simulation, you end up getting a lot of stuff for free. You just sort of give it these basic properties, and then you move it around, and you end up getting a whole bunch of secondary. It just generally looks better. And so a good example of that is the tentacle beast in Prometheus, which utilized this, and it didn't follow any strict anatomy, but it was built with the system, and it sort of benefited from the fact that you could deal with collisions, and the friction, when it's sliding, when the tentacles slide along the ground and stuff like that.
So where's the edge of tissue, in the sense that, one of the problems that you want in this is to make sure at the point at which there is a pivot, so maybe in an arm joint, we're getting a nice surface that doesn't look oddly creased and oddly buckled. Is that inside tissues constraint to make that skinning work properly, or are you handing it off to some other part of the pipeline?
One of the interesting things with tissue, since we've switched to using this more physically based approach, is skinning sort of gone away in the department. So we don't, for the bulk of the deformations, obviously we have a large toolkit of deformers to do a variety of things with, but the meat and potatoes of the department now is just building the anatomy, and you create these muscles and you attach them to a geometric skeleton, and you build your fat and you build your skin, and then you embed your high-res model into that, and there's no weight painting. It's just embedded barocentrically into that volume, and it just deforms. So it's a direct result of the tissue simulation.
So I can control it as an animator how much I'm picking up the environment's real physics, but can I go over the top and maybe distribute it? I mean, is there any kind of concept of painting over to accentuate because I just want a muscle to behave differently and be more upper arm than lower arm or something?
Sure. I mean, there's a few facilities we have in there for like artistically directing the simulation, if that's sort of the question, I guess.
Yeah.
We early on a like post-based deformation, but not in the traditional sense. So typically, when you think of a PSD, you think of something that's used to sort of blend shapes, in a an n-dimensional space. And we'd taken that idea and then applied it to the shape matrix of the system. So you could dial in a variety of shapes to define what the rest state of the model looks like. So we could go in and you could model a precise shape. Oh, I want this to look exactly like that, and then you can put that into the system, and then you can dial that in, and without making the collisions invalid or changing anything else about the physical simulation, it will still magically sort of look more like something else. Though that's something we sort of have in our back pocket, try not to use too much, because it, once you start leaving, a physical basis, it makes things a little bit harder to, get everything for free. And then the other thing that we've found has worked really well for us lately is our tools for embedding fibers have become much better in the past year or so. So we can actually, embed really complex networks of fibers and achieve, the similar results just by using fiber activation.
So tell me about the building process and how you would build out from something.
Yeah, so typically, we'll, at this point in time, we have quite a large, database of muscles that we've modeled and built over time. But when the first time we went through a full build, we had to have all the muscles modeled and then tetrahedralized and then constrained properly and attached to one side of the character. And that process, that iterative process to get the right behavior, we try to keep that in quite a tight loop. So in order to make things work well and then to be able to then distribute what one technical director learns to benefit all the characters, we early on sort of realized that we need a robust way to sort of take this and apply it to everything. And this has sort of changed the way that sort of people typically work in the department now. As historically, you'd have one person sitting on a character and they would work on that character for the film, and that would be what they did. But it was typically a lot harder to distribute those tasks. But sort of since we've changed this approach, you could have multiple people on one character focusing on different areas, and then everything they learn from that could then be warped and will benefit the whole cast of characters. Like on Avatar, we had Jake who we're using to do all our primary sort of R&D work on, and any of the benefits we got from him, Sute and Natiri would then benefit from that. So, yeah.
So this is based on finite element analysis?
Yeah.
So is it a fixed number of tets, or is it, because I only know finite element analysis from its work in destruction sims, and there, quite often, it's a finite number of tets and it doesn't change.
Yeah, or I guess in our simulations, yeah, once the muscle's tetrahedralized and added to the system, we're not changing the number of elements.
Because there's no need to, right?
There's no need to, yeah, because the body's not changing. But.
And so that one model would normally give enough flexibility for a whole range of stuff. You wouldn't need to sort of worry about doing different, I guess that process of tetrahedralizing the muscles is kind of like a one-off build stage? Yeah,
though I guess the way the system solves, though, there's a variety of sub sort of systems that are solved. Richard, who's not here right now, but when he refactored the work, he sort of as a stage to make it all run faster, sort of sorted out. It figures out sort of per time step what elements are interacting with each other, and then it builds sort of little pools of of matrices that it's solving. And then, they are sort of isolated at that point. So obviously, a muscle on your arm isn't necessarily interacting with one on your leg at the time. So it can separate those in the system matrix, and it can solve those on separate threads and do all that.
So all the finite element analysis stuff I know,
Yeah.
I know from rigid body sims, I know it from destruction sims.
Yeah.
But you're not doing rigid bodies with this.
No. So, I mean, to sort of, sum it up, I guess, is sort of like the top level. So, cloth simulation, fluid simulation, rigid bodies, destructible rigid bodies have all been done on massive scale in lots of movies, right? Like 2012 and all these movies, and they've art-directable fluid simulation, and people don't shy away from fully clothed characters for feature animation or digi-doubles. So what we did was we did exactly that, but for creature deformations. So we took that, it's completely analogous to that. So typically, if you ask somebody to put that jacket on you for a shot, and you said, oh, could you animate every vertex, please? We're not going to do with cloth sim. We're gonna sit there and we're gonna animate every position of every vertex for every pose. That's what our creature setup used to be like. And all we've done is sort of taken that into the same realm as a lot of other effects. We're saying, well, no, all the heavy lifting, so all the interactions, volume preservation, wobble, deformation, all that stuff will be done by a simulation. And yes, there's art-directable tools in there, and there's ways to control that, but ultimately, all our creatures now are the same. It's exactly the same.
And pardon my ignorance, but one of the factors is, there's a full solve of a sim, and then there's a partial solve of a sim, and sometimes, as in many things in visual effects, that last 10% is about the most costly. Is there a sense of being able to partially solve something if it's not like a foreground character, or is there like just one full solve?
Yeah, so that's something that we the PSD we were saying earlier how we use that as a way to artistically drive what the muscle looks like. On occasion we want to do it that way, but we also use that code base for making an interactive cache of the simulation. It's a way to build something that is will run at near interactive speeds, but is 95% what the simulation is, or even better, than probably within 99% of what the simulation is. But it just runs faster.
Plus, you get the advantage, as you were saying before, that the muscles don't necessarily all interact with each other, right? So you can have quite a lot of muscles or tendons or whatever working, but not them all computationally self-dependent.
Yeah, so our simulations get distributed across multiple cores and multiple machines typically, so to help everything go faster.
Oh, and I should have said it at the start, if you want to follow us on Twitter, and you are not, we are at FX Guide News. Or on Facebook, just go to facebook.com/FXGuide, where we post not only FX Guide, but also FX PhD news and updates. Well, until next time, see ya. For more industry news, in-depth features, podcasts and forums, check out fxguide.com. And for visual effects training, check out fxphd.com.